Abstract class. Abstract class is a special base class which contains at least one pure virtual function. A pure virtual function is a function that is declared in the base class and defined in the derived classes. We specify a pure virtual function by using the pure specifier equals 0 as part of declaration of a virtual member function in the class declaration. Remember how in program 66, our last coding example, we had declared the base class named Polygon, which had a virtual function named area function. We have a return 0 statement in there. Hence, this virtual area function is not a pure virtual function, and this base class Polygon is not an abstract class. Let's modify the above class Polygon. I edit virtual area function with a pure specifier equals 0 as virtual int area function equals 0. Now, the virtual area function becomes a pure virtual function, and the base class Polygon becomes an abstract class. Notice how we appended equals 0 to virtual int area function instead of specifying an implementation for the function. This type of function is called a pure virtual function, and all classes that contain at least one pure virtual function are the abstract base classes. The major difference between an abstract base class and a regular polymorphic class is that, in abstract base classes, at least one of its members lack implementation feature, and we cannot create instances or objects of an abstract class. However, we can create pointers to an abstract class and take advantage of all its polymorphic abilities. The declaration Polygon P is not valid for an abstract base class because it tries to instantiate an object. The declaration Polygon star PT1 is valid for an abstract base class because it's a pointer declaration. Hence, for an abstract class, pointers to the abstract base class are used to point to objects of its derived classes, and thereon, to implement its polymorphic functions. Abstract classes are best used in data abstraction, where developers have the option to hide code implementation details. Let's next edit program 66, which we had seen in our last video session, and apply abstract classes to it. It's quite simple. A two-step process. As just shown in the last frame, we need to edit the virtual area function with a pure specifier equals 0 so that the base class becomes an abstract class. And then, we will be deleting the base class objects. I mean, delete objects created from the base class, Polygon, and create references only via derived classes. Not to worry, nothing complicated. So here is our program code. It is similar to program 66. Differences are on line 10, where we edit the virtual area function with a pure specifier equals 0. Then we remove base class object P on line 27, and other related statements. We retain the rest. So once again, let's quickly track the flow of program control. Here is the class Polygon. Protected variables, width and height are declared. Public function setValues is defined. It assigns values to width and height. Next we have the public virtual function, area, which has been assigned the pure specifier equals 0. Class rectangle, that inherits from class Polygon, is declared. Its area function returns the value of width times height. Class triangle, that inherits from class Polygon, is declared. Its area function returns the value of width times height, divided by 2. In the main function on line 26, we instantiate object R for rectangle and object T for triangle. As per line 27, pointer P1, pointing to base class Polygon, is assigned address of object R. So it points to block of polygon within the object R. As per line 28, pointer P2, pointing to base class Polygon, is assigned address of object T. So it points to block of polygon within the object T. On line 29 of program code, we instruct pointer P1 to execute its setValues function. So in object R, setValues function executes. 4 is assigned to width, and 5 is assigned to height within this object. Similarly, on line 30 of program code, we instruct pointer P2 to execute its setValues function. So in object T, setValues function executes. 5 is assigned to width, and 10 is assigned to height within this object. Program control shifts to line 31, where we have instructed to output the area of a rectangle by invoking the area function that pointer P1 is pointing to. And then on line 32, we have instructed to output the area of a triangle by invoking the area function that pointer, P2, is pointing to. The program ends. So we learned here to declare an abstract class and point its virtual function to polymorphic functions within its derived class objects. Let's next look at this pointer. This is a pointer that points to the object within which the member function is called or invoked. When a member function is called, it is automatically passed an implicit argument, this pointer, which is a pointer to the invoking object. If you remember, in program 60 we had used it in the unary operator function to calculate net salary from given gross salary after tax deductions. Here is the unary operator function which we had defined, where net salary is the class, and minus operator is the function. The minus operator function returns back this very same class as the result. And hence, we had used the return star this statement. What did it do? It returns the reference of class object within which this function resides. Note. Number 1, friend functions are not members of any class, and so they have no this pointer. Number 2, static member functions do not have a this pointer. So with this, we come to an end of this chapter on polymorphism. I hope these sessions have been helpful to you. If you have any doubts or need clarifications, you are always welcome to contact me. I wish you a very bright future. Take care.